Morning, everyone. I hope everyone had a good holiday and welcome to our fifth exercise session. Today we'll be discussing about perceptron algorithms, and those tips have already been uploaded there last week. Um, so we can refer to the lecture slides on page 8 to 15. There are some instructions about the perceptron algorithms. First, let's take a look at the exercise questions. For our task today, we need to implement perceptron classifier and use it to classify and or um, and exclusive or data shown below in the same order. We can start the algorithm with the small random weights. Stop algorithms after fixed number of iterations. A correct implementation should achieve 100% accuracy with and or data, but not with exclusive or data. Why algorithms does not reach 100% with this set of data? Visualize and report what happens to perceptron weights if you keep updating them for exclusive or data. As we have seen from the tips, we can take a look at page 8 from the lecture slides. This has already been discussed during the lectures by Professor Gao, so we'll go through them very quickly. Here are the perceptron learning algorithm that we'll be implementing ourselves. So we will now use the library. We will implement the algorithm ourselves. Okay, first we implement the libraries that we will be using. We use NumPy and Matplotlib for visualization. Here we have three logic gates. And in digital gates, those three fundamental gates are the gates they take binary inputs, such as 0 or 1, which represent true or false. Then the gate will produce a single binary output based on the rules they have defined here. And here we have three gates. The first is the AND gate. So the output is 1 if all inputs are 1. Otherwise, the input is 0. And you can also think of this as two light switches connect to the same bulb. The light bulb is only on if the switch A and B are both on. And the same analogy goes to the other gates. So for the OR gate, the output is 1, which means true, if one of the input is true. So if one of the input is 1, then the output is 1. From And if both of them are zero, of course, the output is zero. And for the exclusive OR gate, the output is one if the inputs are different, which means if one put is one and the other input is zero, output is um, then the output is one. And if the outputs are the same, if they are both zero or if they are both one, then the output is false. For our AND gate, the data is linearly separable. You can draw a straight line on a graph to separate the point 1, 1, which gives the output 1. And for the OR gate, it's also linearly separable. But for our exclusive OR gate, the data is not linearly separable. If you plot those points, you cannot draw a single straight line to separate the points where the output is 1 from the points where the output is 0. And after those background knowledge, so we can actually already predict what our graph is gonna look like, because we know the exclusive OR gate is not linearly separable. So we know it's not gonna achieve 100% accuracy on the exclusive OR data because it requires a nonlinear boundary. And about the perceptron algorithms that we will implement, the perceptron algorithms, I think it has also been discussed in the lecture. It's one of the most simplest types of neural networks. It's basically a linear binary classifier, which means it tries to find a straight line in a 2D data, but if it's a 3D data, then it's a plane or a hyperplane in a higher dimension. And it uses this straight line or a plane or a hyperplane to separate data points belonging to different classes, which are usually just labeled as 0 or a 1. It takes binary inputs and it multiplies each input by a specific weight. And the weight represent the importance of that input. It sums up the weighted inputs and it adds a bias term. And if this sum exceeds a certain threshold, then the perceptron fires, which it will output 1. Otherwise, if it doesn't fire, then the output is 0. So the here we can see the perceptron learning algorithms. These are the formula that we'll be using. The perceptron learns by adjusting its weights and bias. So it looks at one training example at a time. If the output matches the correct label, then it doesn't do anything. But if it makes a mistake, it adjusts the weight and the bias slightly to make the specific example that are more likely to be classified correctly next time. Here are the learning algorithms. Let's take the learning algorithm. So the core idea of this weight update is the new weight equals to the old weight plus learning rate that are multiplied by the difference between the correct output and the predicted output. Here, d minus y. Here we have the correct output. We minus the predicted output from it. Then we multiply it by x, which is the input value. So the old weight, the learning rate, the difference between the correct output and the predicted output. Then we multiply it by the input x. And that's how we get the new weight. The learning rate here, learning rate, just as its name sounds, it controls how big the adjustment step is. So a smaller learning rate means slower learning, and a larger learning rate means faster learning, but it can overshoot sometimes. And by minusing the predicted output, we get basically the error that we get here. If the prediction is correct, then the error will be 0, so there's no change. But if the algorithm predicts 0, but the correct output is 1, then the error is +1. So the weight associated with the positive inputs are increased. But if it predicts 1 when it should be 0, then the arrow here is -1, and the weight that associated with the positive inputs are decreased. And that's basically the learning rule. And to implement it, we define a perceptron function. We need x input, y input, prediction, y input, and learning rate, iterations, in initial weights. Okay, the first thing that we need to do is that we pass the initial weight if it's used. So if initial weight is not given, then we create a weight vector. So if W is none, so the size, if the size is number of features in x plus 1 for the bias term, weights are initialized to very, very small random numbers. That's why we multiply it by 0.01. So it will be a very small random number. And then we need to add bias term to input x. So here we are propagating ones, a column of ones to the input feature matrix X, and this allows the bias weight, which is W, to be treated like any other weight during the dot product calculation that we will do later. And we initialize a variable to store accuracy. Okay, then for the training loop, I think the connection dropped. Let's see if it's still recording. Yeah, it's still recording. Okay, for the training loop, for I in range of iterations that we have defined earlier, which will be 20 if it's not giving a specific number. This is the first prediction step. The x dot w calculate the dot product for all input samples. So this is the core linear operation, which is the sum equals w1, w01, w0 multiplied by 1 plus w1 x1. And add w2 x2. Then we compare it if it's larger than 0. So if the weighted sum is larger than 0, then the output is 1. Otherwise, it's 0. And then because it's a comparison, the result will be a Boolean type, true or false. We use S-type to integer, then we'll convert the Boolean result to integers. So it will be 1 or 0. And this is the weight update step. We already explained how the algorithm update its weight, and y minus predict is creating the error for each sample, which is the algorithm here. In the algorithm here. And it scales the adjustment by the learning rate, which is represented here. And then we add the calculated adjustment to the current weight W. After we have updated the weight, then we can calculate the accuracy. So again, we're comparing the prediction with a true label, with the true labels. And then we calculate the proportion of the correct predictions by using the mean function. So we get the accuracy. And we return the weight and the final learned weights and the accuracy. Okay, this is the basic, very, very simple neural network of the perception neural networks that we have implemented. Um, let's go back to the exercise. So we will input those gates, those data into the perceptual algorithms that we have defined here and classify them. So then first we need to prepare the input data. We'll create a NumPy array. So all the inputs are 0, 0, 1, 1, 0, 0, 1, 1, 1. These are the input data. And we set the type to float. So it contains all 4 possible pairs of binary inputs. And this, it seems the internet connection is not very good today. Okay, these are the 4 possible inputs, and it represents the standard inputs that we feed into the logic gates. And we specify a flow. We specify that these numbers should be stored as floating points instead of integers. And that's very common practice in machine learning algorithms, even if they look like integers, but we should store and calculate them as floating points. And then we need to create the NumPy array holding the correct outputs for each operation. Okay, let's check if those are correct. 0, 0, 0, 1. These are the outputs, the Y label. 0, 1, 1, 1, 0, 1, 1, 0, 0. Then we can just pass those inputs into the perceptron algorithms that we have defined earlier. So um, we pass the input data which is the binary X. Here we pass the input data and the desired result. The perceptron function will run its training loop for the default 20 iterations. It tries to learn weights that map the inputs to the correct outputs. Then we return the final learned weights and the final accuracy. So the next thing that we need to do is just to print out the accuracy result. Okay, maybe we have made a mistake in the perceptron algorithms. Let's take a look at the perceptron algorithms. Looks like we have made our shape here is probably not correct. The prediction as told as in it. Accuracy. Oh, okay. Looks like yeah, it looks like it's here. The shape was not correct. Okay, why is this still giving this red line? Okay. So the our initial the shape of the weight was not correct. That's why it couldn't run. And now after we have fixed that, we can see the accuracy for and or. We reached 100% accuracy, but for exclusive or, we will only get a 0.5 accuracy. And is the result that we have discussed before because AND and OR gate are linearly separable, but for the last gate, it's not linearly separable. So the single perceptron cannot find a perfect linear boundary to solve this this classification problem. And for our second task, we need to use the bogus student data. We train a perceptron to classify students with grade 0, 1, or 2 from the rest based on the exercise and the exam points. Adjust learning rate, number of iterations, and initial weights to reach 80% or higher accuracy. That's the target of our algorithm, of our result. We need to aim for 80% accuracy. We visualize the learned weights by drawing the data and the learned decision boundary. Do you think the results are good? Could they be better? Why the learning algorithm did not reach a higher accuracy? And here are some tips for the visualization. The decision boundary is the line here, where x1 and x2 are the input variables, which are the exercise and exam points. We fix x1 and solve for x2. So the formula for the decision boundary is given in the task in the task. Let's just get started. We first input the data. We have used this data set before. Is it here? No. And let's check if it's correctly imported. So the names through here are telling the function that the very first row of the file contains these headers for the columns. So it allows you to access the data in each column using its names later. Um, Here we're taking the sequence of arrays, which are the two columns, and drawing them along a new axis. The NumPy stack takes the sequence of the arrays and join them along a new axis. So by default, it stacks them vertically. It will create a 2D array with two rows, one for exercise points and one for exam points. That's why we need to perform this. We need to transpose them. We need to use the transpose operation on the array. So it swaps the columns and the rows and the columns. And that's the result we get here is a 2D array where each row represents a single student. So the columns are exercise points and exam points. And if we didn't do the transpose, you can also see the result. And that's why we need to transpose them. for easier manipulation later. Um, Here we need to compare. So we def we need to compare as larger than 2 because we need to classify a perceptron, or classify students with grades 0, 1, and 2 from the rest of the result. So we compare it that's larger than 2, so it doesn't include 2. And then we change the type to integers. So first we are accessing the columns in the grades column, the data from in the grades column, and then we're comparing them if it's larger than 2. And then it will create a Boolean value, and we are converting the Boolean value to ones and zeros. So basically it says this student's grade is larger than 2, or is not larger than 2, is larger than 2, larger than 2. Then we can start to call the perceptron function to train a classifier. Maybe not so many iterations. Okay. Um, we'll be experimenting them with different learning rate, different iterations, and initial weights. But first, let's see how well it did for. Let's see how well our first classifier did, and we can see the accuracy. So here we saw that for our first classifier, we changed the iteration number to 100. The default is 20, and the accuracy is around 73%. What if we only iterated 20 times? The default iteration is 20, so the accuracy is only 37. So by increasing the iterations, we can improve the accuracy. But what if we adjust some other parameters? For example, we adjust the learning rate. The default learning rate, I think, is 0.01, and we decreased the learning rate to 0.001, but kept the same iterations, and the accuracy improved as well. So not only the iteration can affect the accuracy, but also the learning rate. And often if we change the learning rate to 1000, we can see the accuracy improved once again. Often when we increase the iterations, it's also necessary to use a smaller learning rate to allow the algorithms enough steps to potentially converge. But how can we improve the result even further? This time, let's try a given initial weights. Maybe even a smaller learning rate. And the way we're given is minus 50. And 200. And here we can see the after after giving after giving the initial weights, the accuracy changed again. But what if we give a really, really small learning rate? Can it improve the accuracy? And here we reached 99.35% of accuracy by giving an initial weight, even though the learning rate and the iterations are kept the same as the second classifiers. So we can see the initial weights really affects the accuracy as well. So that's the importance of initialization, because all the first and the second classifiers we used random weights. We use random weights. And algorithms like Perceptron is very sensitive to the initial weight parameters, especially on data that isn't perfectly separable or when the number of iteration is fixed. So this initial starting point allow the algorithm's weight update to converge towards a very accurate negative slope. And by adjusting the learning rate, those different hyperparameters, we reached an accuracy that's higher than 80%. Do you think the learned weights are good? Could they be better? Why the learning algorithm did not reach a higher accuracy if it was below 99%? I would say this accuracy is very good. The accuracy, it means the decision boundary defined by the third classifier are correctly classified over 99% of the students into the right category. But let's see if we can get even higher if we increase the iteration. See, we even get a 100% accuracy here but it depends on your computational resources. If you don't have as much resource, um, then you might not be able to use such a large iterations. Here we have a very small data set. We can do that. But if you have a very larger, if you have a larger data set, then this change will be it will be 10 times longer than the second classifier. The time it take would take the time it, on training the classifier would take 10 times more. And for W1 and W2, we will say the first one, it didn't have enough iterations. That's why it has a low accuracy. And the second one already improved a lot. But maybe it's still not enough iterations and the learning rate is already very low, so that's good. But maybe the iterations wasn't enough. That's why it didn't get a high enough accuracy. Okay, then we need to visualize the result by drawing the data and the learn decision boundary. Here is already giving you the formula for the line. Okay. We define function to plot perceptron. We need the learned weight. Okay, first we need to create a range of x values that represent feature. The two features access representing feature one, which is the exercise points. Here we have a linear space that generates 100 evenly spaced points between 0 and 20, which are the exercise points, because remember the exercise points ranges from 0 to 20. The highest you can get is 20 points. And then we calculate the corresponding y values, which represent feature 2, which is the exam points. And that line lies exactly on the decision boundary. So the decision boundary formula I have given here already. And we can take a look at it, like how we can solve it. It's already given a tip where x1 and x2 are the input variables, fix x1 and solve for x2. And let's take a look how to solve this formula. So W0, x1, uh, to plot this line, we need it in the form y equals something, right? So we need it like this, y equals something. Here's already calculated for us um the autocomplete, the AI already calculated for us, but we need to learn how to solve those ourselves, and it's not hard. Where y so we need in this format y equals something, where y equals corresponds to x2, which is the exam points, and x corresponds to x1, the exercise points. And basically, we just need to rearrange them a little bit. We use very simple algebra to get x2 by itself. So first, we move the terms without x2. So we move this part to the right side. This is just simple algebra. So the term we isolate the term without x2. And we move this side to the right side of the equation. And then we divide it. And then we divide by W2. And that's how we get, and that's how we get in the format that we want, which is this one. Oh, sorry. When um when you move this, it should be minus. And then we just change the minus number to x2. To W2. Okay, and that's how we solve this equation. And we get it in the format that we want. So W0 added by W1 and multiply it by x range and divide it by W2. Then we plot the line using matplotlib. Okay, then we just need to create a figure verse. And then we first plot the data. We use a scatter plot. And here we can see these are the distribution of our bogus student data here. Maybe we have plotted this before. So we are selecting all the rows from the column 0 of the data x. which corresponds to exercise points. And we're selecting all the rows in column 1, which corresponds to exam points. And they are plotted on this is the x-axis and this is the y-axis. And because data y, the data y contains zeros for grades that are less than 2 and ones for grades that are bigger than 2. So we use it. C represents color, and we use it to color those points, which means those people in yellow, they got a grade that's larger than 3, including 3. And those people got 0, 1, 2, and those people got 3, 4, 5. And then and when you see the graph like this, you can clearly see the decision boundary lies somewhere here, right? Because here, the line here is where it separates the two classes. But now let's plot the lines from our classifiers. Okay. Let's add a y limit. Let's focus on 1545. So this is the line from our first classifier. We can see the result is not, the line is not so correct. That's why it only has an accuracy around, it has a high accuracy, 73%. But it's not good. It's not super good. Then we plot the second line. You can see it got better, but it's still far away from the very good line, the correct line. And for our last line, this is the line that achieved 100% accuracy. But there are some here you can see there are some overlaps, but I think it's just because the size of the node is a bit bigger. But this is the line that accurately separates the two classes with very high accuracy. And then we can add a legend. So these are the data and the W1, W2, W3. Okay. Then we have visualized the learned ways by drawing the data and the learned decision boundary. We explained the plotting of the perceptron, the perceptron algorithms. And that's it for today's exercise. We finished 2 tasks. If you have any questions, please send them in the chat, or you can turn on your mic, or you can send me an email as well if you don't want to ask them now. But Please let me know if you have any questions. But if you don't have any questions, then that's it for today's class. Um, and also just a reminder that I think you should get started by preparing for the group presentation and register your group before the deadline. I think the registration form is already open. Please register before the deadline. Let me check when does it end. The the registration for the deadline is 11th of May. 11th of May next month, Sunday. So please register before then. If you haven't started preparing for group presentation, please start right now. You can, if you have any articles that you are interested in, you can send you can send a post in the eLearn forum to find other people who would like to join you. Okay, if you don't have any more questions, then that's it. That's all for today's session. Thank you so much for coming and have a nice week. Thank you.